How are we feeling today?
Tired, hungry.
That seems to be the trend pretty much any class that I have.
I'm just kind of here.
Huh?
I'm just kind of here.
You're just kind of here?
Yeah, I'm tired.
I feel you. At least we're halfway through the week. Today I have something a little different. We have a bit more interaction in the activity today, so I think you're going to enjoy that. What I want to start out with is, again, reminder, make sure your phones are away. I don't want to see it. I don't want to have to send it to the office. Just pocket or backpack. Just leave it away. What did we talk about last class? Last class was also a little odd, but what were we talking about? Huh? Measurements. Good. What did we measure? Paperclip, right? It was a weird task. I told you guys to measure the thickness of this paperclip. What was the measurement tool that I had you guys use?
Dial caliper.
Well, ruler first, right? Dial caliper, yeah. But I started with a ruler. Why was this hard to do? Yeah. Yeah, it was really hard to actually measure because on the ruler, the smallest measurement that I could read is a 1/16 of an inch. Well, this is smaller than a 1/16. So when you go to measure it, you were either having to say like, I'm going to just round up to a 1/16 of an inch, or you'd have to actually like eyeball it and guess. Like it looks like about half of a 1/16. So I'm going to say 1/32. But you were guessing because your instrument wasn't very precise. A couple of things that I pointed out by doing that, again, it sounded weird, but the one thing that I pointed out is your instrument, your measurement instrument is important, right? I measured the exact same thing, but I used a different tool. I used the dial caliper, right? That was a much more precise instrument. So that let me get a much more accurate reading. Yeah, it was 0.43. Yeah, 0.043. So the ruler could only measure to a 1/16 of an inch. This can measure to a 1,000th of an inch. So I have much more precision and accuracy using this. Did I get the correct measurement with this tool? Did I know exactly the thickness of this paperclip when I use this tool?
No.
Are you sure?
No, but once that was sufficient enough for the graph that we had to fill out.
That's a good point. He said it was good enough for what we were using it for. But technically, there's no way I'll ever get the exact measurement. Wouldn't I have to literally count the atoms to know exactly how thick this is? Well, I'm not going to get I think they're electron scanning microscopes. I don't even know if they can look at atoms. It's unreasonable to know this. The other thing, the extreme point I'm making is every time you measure something, it's always a guess. It's always an approximation of the true value. I would need to know this measurement to like 20 or 30 decimal places, maybe even more. Same thing is true. Kyler pointed out, what purpose are you measuring this for? Well, in this situation, this could have been, say, like a pin that I slide in to join like a hinge. Well, my opening, right, the hole that I need to fit this in, like I can't be off more than, 1/100th of an inch. Well, shoot, if I use a ruler to confirm this, I'm making a terrible decision because I can't even get an accurate measurement. I would need the right tool to get to 1,000th of an inch to say like, yes, this part will work because I can measure even more accurately than the 100th of an inch that I need to know, and in order to see if that part fits so that my object can function properly. I gave you guys the example when I cut a 2x4. I want a 4-foot board. This is a terrible choice to measure 4 feet. There's 2 reasons why. What are the 2 reasons why this would be a bad choice to measure out a 4-foot board?
It's not big enough.
That's the obvious one. It's not big enough. This only measures just 6 inches. So I'd have to try and measure 6 inches and mark my spot. Measure 6 inches, mark my spot. It'd take too long, and I'd probably mismark where I stopped. So then I lose my precision anyway. What's the other reason this would be a bad choice to measure like a 2x4 length?
It's not made for that.
Yeah. This is not made to measure long distances to the thousandth of an inch.
You don't need it that precise.
Yeah, I don't need it. That's exactly right. If my 4-foot board is 4 foot 1/8 of an inch, I don't care. I just need the board to stand up because I'm going to screw something in on top of it. If it's a 1/16 of an inch short, I don't really care. For my purposes, I don't need that much precision. I don't need it to be that accurate. The same thing is going to be true. We'll come back to this idea when we look at tolerances. That tolerance is basically where you say this part needs to be 1/2 inch plus or minus a quarter of it, or that's a terrible one. Plus or minus, say, 1/10 of an inch. Right? It could be 0.6 or it could be 0.4. As long as it's in that window, it'll work. That's your tolerance. And we're going to talk about that. That tolerance would tell you if you need to check your part, well, if it's within 1/8 of an inch, I can use my ruler easy. I can be that precise. If it's within 1/100th of an inch, I need to have this to make sure that I'm within tolerance. So we'll talk about that. What I'm going to do today, I'm going to carry on with this theme of measurement. What we're going to do is we're going to actually take measurements ourselves. What I have are, there's this part that was made, right? This part is made. The problem is they gave us only dimensions for the locations of all these holes. We don't know how big they are. So what you guys are going to do today is you're going to take this part. Again, you'll be in groups. You're each going to get a dial caliper. Now, I need you to be very careful with these. These are like $45, $50 a piece. Be gentle with them. They're very delicate. Like, don't quit, I saw other kids take this and just slide it all the way. Like that's terrible for the mechanism inside that makes it work. You use it by taking your thumb. You roll this wheel and it spreads it apart. Go slow, right? Be delicate with it. When you have these holes, these prongs on the top of it, when you measure, they move outward. Well, that's what's going to let you measure edge to edge inside that hole, and then you can read off what it is. When you read it, on the very bottom here, written on the metal like this shaft, this is the first decimal place. So right here, I can see the complete 1 and the complete 2. So I know my measurement right now is 0.2. On the dial, the face, that's where you have the other 2 decimal places, right? So this number says 29. So my measurement is 0.229, right? So that measures all the way to the 3 decimal places. This is your first decimal place on the ruler itself. You need to be able to see the full, from 1 to 2 in order to say, yep, it's 0.1. And then the last 2 decimal places you read off the dial. And if you need help, I can walk over and show you exactly how to do it. But all you're going to do is I have a sheet with the position dimensions. What you need to do is add the diameter dimensions. So you're going to measure each hole, record it, and note it on your sheet so that you have the full part dimensioned on your sheet. You're going to do that as a group. Then what you're all going to do is you're going to take those dimensions and you're going to make this part. Well, you're going to have all the dimensions there, so you just follow, like, my square is this big, this square is this big, and it's located here. Cut that out, cut this out. I just measured the diameter of my hole, right? So I'm going to put my holes the right size in the right spots, make this part. Then you're making a multi-view drawing, which we know how to do. We know that shortcut, right? And then dimension them. Well, the dimensions are easy. Whatever dimensions you have on your part that you use to make it, those are the important dimensions that you want on your multi-view dimension drawing. So today, by the end of class, and I'm probably going to open it up till midnight tonight. Last class, they were struggling with finishing it or moving slow. So what's going to be due for this assignment is the PDF dimensioned multi-view of this part you're going to make a model of. But first, you got to dimension the holes, right? That's what we're doing today. I want to pause and give you guys some background, because another feature of this class, another big theme that we're going to be learning about is holes. In Onshape, in your 3D modeling software, there is a holes command, right? You guys, instead of making a circle and then extrude removing that to make a hole, to make the hole, you literally just place a dot on your sketch, literally a point. That point is representing the center of your hole, and then you use this hole tool, and you say, hey, I want to make a hole, and it'll ask, where's the center of that hole? And you click on the dot you just made, the point. It'll make the hole, and it'll give you a whole bunch of options. It's all right in one tool that'll make your hole whatever you want it to be. Now, what I'm going to throw up on the screen is the introductory material to this assignment, and I want to go through it with you. Where is it? Right here. Because I want to make sure that we're all on the same page. When we talk about holes, there's different types of holes, there's different features, and there's different ways to describe them. The different symbols and annotations we use. The first thing I want to point out, there's two basic types of holes, a blind hole and a through hole. A through hole sounds like exactly what you think it is. It goes all the way through the part. It starts on one face of the part and goes all the way through out the other side.
So kind of like with that dimensioning activity, that weird little object that we made with the hole going down the middle.
Yes, because if you looked down that hole, I could literally see through the part, because it went all the way through from one face to the other. That's right. We've seen one before. The other type of hole is literally just a hole that doesn't go all the way through. Those are called blind holes. It's blind because if you put something in that hole, you don't know where it's going to end up. That's why it's called blind. It basically is just a certain depth in your part that hole goes. That's what you call a blind hole. Here are some more variations of holes. These are all through holes. You see they go all the way from this surface out to the other surface. They go all the way through. Blind hole. They stop in the part somewhere. Have you guys ever seen these? Counter bore and counter sink? You guys ever heard of those? They use those in manufacturing especially, but also like construction. A counter sink hole is basically like this cone that gets carved out of the top of the hole. It creates like a bowl. Some people have said like, oh, I remember that because it looks like a sink. It's a great way to remember it. What you use that for is if you want to make a hole and you're going to drill or put a screw in that hole, this countersink holds the head of the screw, so when you screw it in, it's flush with the surface. And you don't have to drill the screw through the wood and bust it to just be flush. It'll sit nice and clean in that countersink. What do you think a counter bore is used for? Counter bore is basically like a bigger hole that you put only in the top part of your hole.
Bolts.
A bolt, right? You have a bolt, it's got a big hexagon head. Well, if I want a bolt to go in this hole to link two parts together, I don't want that bolt head sticking out of my surface. I want a smooth surface. So what you do is you make a counter bore. It's a bigger hole that's the same size as your bolt head, actually a little bigger, so you can get the socket in there. But that way when you screw your bolt in, the bolt head sits in the counter bore and then it's smooth on the top. So that's the easiest ways that these are two holes are used, countersinks and counter bore. You can see the profile. A counter bore is just a bigger hole on the top of the actual hole. Countersink is like this wedge cone shape, again on the top of the hole. If you don't have anything, it's just called a simple hole. It's literally just a hole through a part or a blind hole. All right? Now, there's specific notation that we use that you guys need to be aware of, particularly when you make your drawing. You have to know what these symbols mean. You guys have seen this one, I think, a little bit before, right? Have you ever dimensioned a circle? Like the cylinder? When you dimension a cylinder, it'll give you this symbol and then a number. Well, this symbol is the diameter. It's telling you the diameter of something is blank inches or blank measurement. This symbol is indicating the depth of the hole. So if you have a through hole, you could put this symbol and then say through. They typically abbreviate it THRU. Otherwise, if you had a through hole, you could just write through. You don't need the symbol. But if you have a blind hole, your hole goes 1 inch deep into the part, you would have to specify, hey, this hole has a depth of 1 inch. You make them. Nice. Countersink, this is a symbol to indicate, like, hey, this hole has a countersink. Right? Makes sense. It's that cone shape. They're pretty self-explanatory. The counter bore, right, the bigger hole, that's the symbol that we use to indicate this hole has a counter bore. This would be an example. In your 3D modeling software, again, this is Fusion 360. It won't look the same because we're using Onshape. This is what you would type in when you make the hole. You're going to set all these parameters. You're going to enter in all this information. Well, when you go to make your drawing and you dimension that hole, this is what you're going to write out. Someone's going to get your part and see this stuff and be like, okay, I know what this hole looks like. I know how I could make it. This says that the diameter of your hole is 0.375 inches. That's right here. The diameter of the main hole. It's a blind hole, so it's a certain depth. And it said the depth was 2 inches. Well, boom, right here. You said from start to finish, the hole is 2 inches deep. Down here, you said, wait, this hole also has a counter bore with a diameter of 3/4 of an inch. Well, right here, your counter bore feature, you defined as having a diameter of 0.75 inches. And you told me that counter bore is 1/2 inch deep, right? How big your socket or the nut would be. 1/2 inch. All that information is really compact and easily communicated. That's why you do this rather than write out diameter equals 2 inches. Depth is 2 inches. These are the notations we use in engineering drawings. Here's another one. Here's a countersink. The diameter is 1/4 inch, right? The blind hole with a depth of 2 1/4. This tells you, hey, there's a countersink, and the diameter of that countersink is 1 inch. Also, they list the angle of the countersink. You can change how shallow or narrow that countersink, bowl is by setting an angle. So that's the whole notation that you'd list. The first line is always the main features of the hole. The bottom line is the specific details, like the counter bore, the countersink. So what I want us to do is see if we understand how to write these out. How am I going to write the drawing notation to describe the dimensions of this hole? What do I need to start with? The diameter. Remember our symbol? It's a circle with a line through it. What is the diameter of my hole? 0.5, right here. So I say diameter is 0.50. What else? What do I need to tell someone about my hole next? The depth. That's my symbol for depth. How deep is my hole?
All the way through.
It's a little tricky, right?
It's all the way through.
The depth is all. That's a through hole. I said go through everything, right? Drill through everything. So this, you normally write THRU. They always shorten it just to make it easier. Do I need to describe any other features about my hole?
No.
You sure?
Maybe. I don't know.
Countersink.
Heard a couple of you guys say it. I need to tell them, hey, there's a countersink. This is not just a simple hole. There's a countersink. What's the diameter of my countersink? Got this. 1 inch. My countersink is 1 inch in diameter. And then technically you do, for countersinks, you'll specify the angle. The reason this is important is someone's going to get your drawing. They're going to see this. If they're going to make the part that you modeled and made a drawing of, if they're going to make this hole, they need to know, hey, where is this hole located? This far over and this far up. They need to know how big the hole is and how deep to drill it. They also need to know, oh, I need to go back and I need to add a countersink. How big a countersink are they wanting? Oh, they told me it was 1 inch and 82 degrees. If they know all this, and again, the additional dimension of where is that hole located, they can make your part. If you don't include this, they're going to look at your drawing and laugh at you because you didn't tell them what they were supposed to do. They can't read your mind. That's the importance of an engineering drawing. It communicates information to either a client to tell them about that product or to the manufacturer, the machinist, whoever's making your part. They're the ones that are actually going to turn it into a reality. They need to know that information. All right, let's do one more. No, this one. That one was too easy. What do I start with? What's the number one piece of information my hole needs to have? Diameter. I need to tell them how big the hole is. How big is it? Down here, 0.25. How deep is it? Yeah, my depth, start to finish, 1.75. I got a counter bore, don't I? So I need to tell them, hey, there's a counter bore. The diameter of that counter bore is, bingo, then I need the depth of that counter bore, don't I? I need to tell them, hey, make this counter bore this big, but I need to tell them how deep to go. 0.37, whoops. Bam. If they have this information, they can make your hole. That's the whole point of putting these dimensions on there. Communicating that information. This you don't need to worry too much about. This would basically be like if you had a screw in your blind hole. Well, the tip of the screw comes to a point. If you want a nice, housing for that screw to sit nicely in, rather than just ramming through the wood, whatever you got, that's what this angle is. But that's like really particular. We don't really go that deep into detail, so we don't need to worry a ton about that. But just know that's what that number is sitting out there. Is there any questions about the hole, or hole types, hole dimensions, how we describe holes, the symbols we use? All right, before I turn you loose, I want to again remind you guys, when you go to make this part, there is a hole feature in Onshape. You don't have to use that, but it will make your life easier if you do, because when you go to add dimensions, if you've used the hole feature, you can tell Onshape, hey, dimension my hole. It knows all of this. Because you made a hole, it can read all of the hole characteristics automatically. The other thing I want to show you is a reminder of when you make a hole, you have to sketch a point representing the center of your hole. Then you need to go back to the 3D model perspective and add the hole using the hole feature. And so I already did that, but I want to show you. What I did is I made a sketch on the top of my cylinder. Oops, sorry. Throw this down so it's easier. I have a clean surface. What I did, I literally, in the sketch tools, I clicked point. It literally just places a point wherever you click. Now in this case, say I put a point right in the center. Say I wanted my point 1 inch above here. I'm going to place my point and then I dimension it. I want to say from here to here, this I want, we'll say 2 inches. Right? I need to fix that point in the correct location. Your sheet will tell you the location of those holes. That's where you place the point. The diameter that you're going to measure, that's for when you make the hole. You know how big to make it. So then what I'm going to do, I finish that sketch. Sometimes you have to show the sketch so that you can see your point. But right here, see this guy? That is your hole feature. That's what you need to use. When you activate it, it's saying, hey, where do you want to put this hole? And you want to say, hey, I want it right here, right on this point. In your situation, you're going to use simple holes today. There's no counterbores or countersinks. I know it's a simple hole. I want it to be a through hole. My diameter, I'm going to say I want to be 1/2 inch. Bam. It made my hole for me. That's also going to be handy when you go to make your drawing. Remember our shortcut. Select the part that you're making, right-click and create a drawing, and you want to select the 4 views. It'll place them automatically, save you some time. In my drawing, there's my hole. If you notice, oh, my view's too small. In the dimensioning tools, there is literally a hole call-out feature. What you do is you literally say, hey, this hole, describe it. It automatically told me the diameter, the depth, and there's no countersink. It does it all in one click. That is why you're going to want to use the hole feature so that when you dimension, you can just call out your hole and have the software get all the notation for you automatically.
Where is that at?
My view smashes it. Your view should show it, but it's near the dimension tool or in the dimension drop-down list. It's called hole callout. You just look for it. It should be listed in your toolbar. My view got smushed when I started displaying, but that will save you a lot of time. That's the correct way to make holes and then to annotate them, dimension them on your multi-view. So I'm going to turn you guys loose. Your task today is measure the holes, get all your measurements, put that part, make a 3D model of it according to your dimensions, make a multi-view, dimension it. Your dimensions are there, just put them on your drawing, and then submit that PDF of your multi-view. The last thing I want to mention is I have a small homework assignment that I'm going to assign that's due before next class. It's step by step. What we're doing today is 1.3.2. All the instructions I just shared with you, but they're also in Google Classroom. Submit the multi-dimension multi-view to Classroom. That's today's assignment. The homework is 1.3.3. This is looking at when you make a sketch, what kinds of constraints can you use to make the sketch look exactly like you want to? Again, it's step by step. Go to Google Classroom and read my instructions first because I cut out like 10 steps. So read those first, then go to my PLTW and follow 1.3.3 step by step. And that one I'm just asking you to do your final product. It's a small extrusion you make. Give me a screenshot of the front view of that. That's all I need. But that homework, that'll be due before you come to class on Friday. So you have like 2 days. Any questions about what we're doing today? Again, virtual students, for this activity in class, you guys don't have the part and you don't have a dial caliper, most likely. So what I did is I attached the answers so that you have the dimensions and you still need to make the part, make the multi-view drawing, and add the dimensions to it and submit that for today. And then the homework you can do all the same, just like the in-person students. Any questions at all? Okay. What I'm going to have you do is get into groups. I have five dial calipers and 5 plates. So I want you guys to come, whatever group you're working with, come pick up a plate. Be careful with these. These are the only 5 that I have. Please don't break these. Be gentle with them. Same with the dial calipers. I only have 5. I might have 6. But don't break these. So come up and get a plate, a dial caliper, and a sheet for your group.
I don't know, like 4 or 5. 7 you think?
Whose group you got?
Me,
Okay, sounds good. You guys will work on this all together. Then the plate and the dial caliper. There you are. You guys working back there? Okay. Trey, who you working with? It don't matter.
And pretty much everybody else joins.
Sounds good. There you are. Anybody else need another? I got one more set. You guys another group? There you are. Yes. Can you put your mask on though? Thank you.
Why?
If you guys want an extra sheet, if you want to take dimensions on 2 sheets, that's fine. Yes, I was going to say, you put that way, please. I need to borrow this for a moment. Are you done with your physics homework, Brody?
Yes.
You did? Did it go okay?
Kind of.
I was hoping it'd be a lot easier this time.
I mean, I got some of it, yeah.
Okay.
Because I was struggling with like, equations and stuff.
Okay.
You should have. I tried watching it there.
Okay, so you guys, I need to, I'm helping you guys out. This worksheet, thank you, is technically saying, hey, get any missing dimensions. It's really misleading. The missing dimensions are the hole diameters. Well, those are easy, but they sneak in missing dimensions for the position that are really hard to, until you start to model it, you're going to realize, wait a minute, I don't know where this hole is. Well, I'm going to give those to you. This hole right here, the position vertically is given. It's 2.875 from the bottom. But it doesn't tell you how far over that hole is. So I tell you from the edge to here, it's 0.875. The other dimension missing is how wide this is. They tell you it's half an inch thick, but they don't tell you how far it is. So I measured it myself, and you guys can just go ahead and write in this length of this hole cutout, this rectangle cutout, is 1.76. And then it gives you it tells you where it's positioned at, right? It tells you this edge is 3.25 from the bottom, so on and so forth. But I wanted to give you some of those very tricky ones that you wouldn't know are missing until you try to model it. All right? Yeah. Oh, how to use it? It's a little odd at first. So if you're going to measure it, which one do you want to do first?
Sir, you want to see
Top left? Oh. This is tight. So what you're going to do, this is 0, 0. What you're going to do, you're going to use these top ones. See, these go edge to edge. This measures outside to outside. These measure inside to inside. So what you're going to do is you're going to stick this in here and pull it apart until you kind of meet some resistance. And then you just slip this out, and then you got to read it. Over here, I can see the 1 start with finish, and I can see the 2 start to finish. So I know my first decimal place is 0.2. Here are the last 2 decimal places. So I read that is 35. So I go 0.235. Inches, correct. Yep. So that measurement you're going to write 0.235.
I have a pretty big forehead though.
So if I measured a hole that big, how big? What's that measurement? Yes. See that like yeah, but tell me the number. Like, what is it? 0. No. This number that you see here, that's the first decimal place. So you know it's 0. This is the last 2 decimal places.
Say that again and I will read more.
Correct. I want to make sure you guys understand like how to read this. But that's a great question. Does that make sense? And then you just measure each hole. What's going on, Drew? Okay. I'm going to have you hop in. Today's activity is small group based. So I would just hop in with you want to work with, and they'll be able to catch you up. Well, basically, how hard we don't know the hole diameter features. We're going to use a dial caliper and measure them. Then we have all the information we need. We're going to make a 3D model of that plate, and then we're going to make a dimension multiple. There's a lot of skills we've done before. It's just now we're using dial caliper to take measurements in order to make a part, and then we're going to use the whole feature, which whoever group you're in, I showed them how to use that whole feature. They should be able to help you figure that out. And then just know there's one homework assignment tonight. It's 1.3.3 on the classroom. Follow my instructions. It's right. So feel free to join whatever group you want, and they'll get you caught up to speed. You guys figure out how to use it?
Yeah.
Sweet. The last thing I want to point out, you also need to measure the thickness of your plate. You see there's an image on the bottom. It's a side view. That's just one measurement that you'll need to make is how thick that plate is. That's going to tell you how far you extrude your sketch that you're making. Yeah. So when you measure the thickness, you want to use these guys because that's outside to outside. Yep. And again, virtual students, you guys are going to be using the answer key that I have posted. You guys are going to use that for this activity since you don't have this plate or the dial caliper.
No.